Yeah. So, okay. So first, I am introducing myself. I am Moina Ghoshal. I am a PhD student at Indian Institute of Science Education and Research, Kolkata. This is ISAR Kolkata, and I have been assigned this course, which is entitled as Fundamentals of Spectroscopy, which was with the course number NOC 23 CY09, and the instructors was Professor Sayan Bakshi and Professor Anirban Hajra. Okay, so this is the assignment of week 2. What I am going to discuss, I am going to discuss some questions regarding to this week lecture, and by from that questions and that understanding of how I am going to solve that, you can solve the assignment problems easily and many other problems regarding that. So actually, I am just briefly recapping what I have discussed in the previous week. That what is spectroscopy and what is a spectrum. Okay, I have told that in whenever you go in chemistry, you need spectroscopy, and then it was discussed about this light matter interaction, and where it was there was two schools of thought. One thought that light is a particle, another thought that light was a wave. So there was a conflict between these two, and there was sufficient evidences for that. And from that, the concept of wave particle duality has came. Then it was discussed about the concept of absorption, stimulated emission, and spontaneous emission. What are the three different parameters? That is called absorption. And two types of emission. One is stimulated emission. That means and which need involves light, which needs some stimulation in the form of light, and another is a spontaneous emission, which is happening randomly or with from ease with its from itself. And then it was discussed about the postulates of quantum mechanics, how they have developed, and then their concept of wave function and what are the properties of this wave function that was also described. Okay, and then the concept of operators and different types of operator and their properties. What are operators? I have mentioned that in for every observable in classical mechanics, in quantum mechanics you will need some operators. Okay, and so this kind of operators, how much different kinds of operators are there, what is their properties, I have also discussed that. And eigenvalue and eigenfunction, some delay questions related to eigenvalue and eigenfunction was solved. Then it was mentioned about the time dependent Schrodinger equation, and a simple model system was taken, which uses the particle in a box, concept of the particle in a box. Excellent. Yeah. Okay, so particle in a box concept was discussed. What is the particle in a box? It was just a model system to give you a brief introduction of how to calculate this wave function or a system. You for this you need to have the boundary conditions. From that you can calculate the energy levels, all that. And also there was a calculation of this energy and also the normalization constant. Then Professor Bakchi has explained about the calculation of this Einstein A and B coefficient, which was for what, and I have explained that for a is something, a constant is something that is no kind of light interruption. That is for spontaneous emission you can use is a coefficient, and for B coefficient needs light interaction. So for B coefficient stands for B12 and B21 and B12 stands for this absorption and B21 stands for stimulated emission. Okay, then it was explained about the condition to obtain this absorption and the stimulated emission. Okay, the absorption, how to in what condition there will be absorption, in what condition there will be stimulated emission. And also there was discussion on the selection rule for electronic transition. Okay, this was the last week assignment that I have also discussed some questions regarding that. Now this week there is a there was the discussion about in the lecture 6, there was a discussion of the concept of transition moment integral, which is a very important thing that we need to and there was the interaction of this electric field with matter and the change in the Hamiltonian of the molecule due to external perturbation like the electric field of light. Okay, so it was also discussed. One second, just yeah. So the electric field of light. Initially, the Hamiltonian was just H naught. Initially, the Hamiltonian just H naught. Okay. But whenever you are using electric field, it is perturbing the Hamiltonian, and there is some term is coming like a V, and which is coming due to electric field of light. They have explained then this whole phenomena is changing, and how this is changing, and how in what condition for a two-level system, how can you find the probability of the system in either of the states? You can easily calculate from that. Okay. In lecture 7, there was a derivation of the equation for transition moment integral, and they have calculated the condition under which the transition will be very much intense in case of two-level system. And there it was also calculated that it needs to satisfy some condition which is known as Bohr's frequency condition. What is Bohr's frequency condition? If we define delta E as the energy difference between two states, sorry, if we explain delta E as the energy difference between two states, if one is E2 minus E1, E2 minus E1, this will be equals to H nu, that is the energy of the light. Okay, this is the Bohr frequency condition, that the energy difference between two levels, if I am drawing if this is E1, this is E1, this is E2, and if this energy difference is H nu, this energy difference, if I name it delta E, if delta E is equals to H nu, then in that condition the intensity will be very much intense for a two level system. So this there is some proof, and there is some problems regarding that I will going to discuss in this assignment solving session. I think someone is joining. Wait a minute. So in lecture 8, there was a comparison of chemical reaction with light matter interaction, how they are interrelated in terms of chemical reaction and the light matter interaction. And from that, Professor Bakshi has shown the derivation of Lambert-Beer's law, which is very important in case of absorption spectroscopy, which is the Lambert-Beer's law. And then from that, the concept of this molar extinction coefficient, okay, from this Lambert-Beer law, yeah, from this you can, it was shown the calculation of this molar extinction coefficient in case which it was shown as the symbol epsilon. Okay, so in case of absorption, you have seen there an equation showing A equals to epsilon Cl. The epsilon is called molar extinction coefficient, and then there was the conversion of this absorbance to transmittance, that was also shown here. Is absorption to transmittance, absorbance to transmittance conversion, which is also included in the next questions. There was, and when that will come, and I will discuss that. Then in the lecture 9, there was absorption spectra with different x-axis. Okay, so in what spectroscopy case, what x-axis will be beneficial? Like if we can take this lambda as the x-axis, or I mean the wavelength as the x-axis, or wave number is the x-axis, which will be beneficial? That different talks was there. And also there was some explanation regarding different types of line shape functions. What different kinds of line shape functions are there? It could be how is a Gaussian function, how is a Lorentzian function, different types of line same functions were explained, and different types of line broadening, like if it is Doppler broadening, collisional broadening, what kind of broadening is happening. That was extremely explained very good. And also there was how what is the reason behind these kinds of broadening, that was also explained in the lecture. Then in the lecture 10, different types of spectroscopic techniques were introduced, and which is related to what kind of range of energy or what kind of range of wavelength in the electromagnetic spectrum that was introduced, in which case which will give information about what kind of spectroscopy, that was greatly explained. Okay. In the lecture 11, there was a discussion about the time scale for different spectroscopic processes, which spectroscopic process takes more time, which is slow, which is fast. That was explicitly explained in this lecture. Okay. And also then at the end there was a concept of Born-Oppenheimer approximation, which was introduced, which states, what does this state? Yeah, this is Born-Oppenheimer approximation. What does the Born-Oppenheimer approximation state? That you can separate this electronic motion, nuclei motion separately. You can treat them separately. If your total energy is the summation of translational, vibrational, rotational, electronic, and nuclear, you can separate them, each of them. Okay. I think yeah. So I'm coming to the question. First question is, the dipole moment associated with a set of point charges located at the position, point charges, which is defined as this one, this, yeah, which is defined as q1, q2, qn, and which is located at the positions r1, r2, rn, such that or summation of all the charges is zero. Okay. In that moment, what could be the dipole moment associated with it? It could it be zero? Could it be summation of all qi into ri, this vector, summation of this one, or it would be y qi ri square, ri, sorry, qi ri, or it could be I and j qi qj into ri minus rj. So what should be the answer? Anybody try? Can anybody try, please?
That will be zero.
Sorry,
Zero.
zero. Any other answer?
Huh?
Anybody else? Okay, so no answer is coming actually. So I'm going to explain that. So you can follow the reference number reference in lecture 6, where it was explained about the dipole moment. Actually, what happens that the dipole moment is actually of a molecule is given by the multiplication of a point charge situated at the distance ri. Suppose I have a point charge here. This situated. This is a point charge. It is situated at this has the charge of qi. Suppose it is situated at distance ri. Okay. So my dipole moment will be charged into the distance. Simple as that. Qi Qi into Ri. Qi into Ri. Okay. So this will be my dipole moment. Now, as I am to getting summation of all that, so in that case, the summation will be like this one. This mu I should be like this mu I should be like summation of all I Qi into Ri. Okay. So that will not be zero because in this case you can see the total charge is zero. But when you are getting this Q1 into R1, this is not zero. Q1 into R1 is not zero. Your total summation is zero. Charge summation is zero. That means
Okay.
yeah,
Yes, yes, yes.
yes.
Got it.
That means you have total charge is zero. That means you have the same number of positive and negative charges. Suppose, but the charges, the individual charges are not zero. The total charge is zero. Okay. So that's why when you are getting this mu will be summation of all Qi into Ri. But that what I have said that this equation is valid only for neutral molecule and atoms. That means when the total charge is zero. This condition is satisfied when this is the condition. This summation of all Qi will be zero. That is a neutral molecule. There is no charge extra here. But if there is an ionized molecule, whenever there is a charge there, okay, yeah. But for ionized molecule, there will be some center of mass. With respect of that center of mass, where is the position of this charge? That will determine that what will be the your dipole moment. Okay. But for neutral molecules, here is since there is no center of mass, as all total number of charges is equals to zero. So in that case, it will be simple summation of Qi into Ri. Okay. Now, since this position vector, it is having since you can see here, it is a vector quantity. So its magnitude as well as its direction is important. That's why we cannot put this mod there. Okay. So you are so what is your correct answer? So your correct answer will be this I summation what all of I it will be Qi into Ri. Okay, fine.
Third one.
Yes, no, second one. Third one is
Second
that
one.
is
Okay.
mod. There is a mod sign, but since it is a vector quantity, you cannot put mod there. Okay.
Okay.
Okay. Do anybody have any questions? Okay.
No, sir.
So
Continue.
I'm moving to the next question. Okay, so next question is which of the following assumptions is usually made about the electric field associated with light while describing light molecule interaction using quantum mechanics? That the electric field causes a small perturbation to the molecular Hamiltonian. Is it the electric field acts along the dipole moment of the molecule, or the electric field is a constant, or the Hamiltonian of a molecule interacting with the electric field is time independent? So, what should be the answer?
In this most probably fourth one is that Hamilton of the
Uh-huh.
molecule interacting with the electric field is time independent.
Okay. Okay. Other answers? Uh, you would want to try? Okay, fine. So I'm explaining that. So you can find this reference in lecture number 6. The reference about this answer. What is said actually? Just let me explain. Then I show you the explanation that whenever there is no electric field, your Hamiltonian was H naught. Okay, and you have considered that this H naught is time independent Hamiltonian. Okay, you have calculated, you have seen for different cases like particular box, you have seen that you have taken this H naught as as a time independent thing. Then you have calculated or done all the calculations. You have calculated this energy. You have calculated the wave function, and then finally you have multiplied with some time term. Okay, but your Hamiltonian in that case was time independent, right? Time, okay, time independent. Okay, so in that case, your Hamiltonian was time independent. But when you are interacting this molecular Hamiltonian, the molecular Hamiltonian, so if you are interacting this with light, then what happens? This electric field of light will cause a little perturbation. This, sorry. So this electric field, suppose I am taking this perturbation as V. Okay, and you have seen that this V, this perturbation due to electric field, you can define it using this V can be defined as V is equals to E is equals to mu into E. Okay. Oh, there will be a negative sign. Yeah. Okay. Now this E for this electric field. Sorry, I'm write it clearly. You can write V. It can be written as minus of mu into E. Okay. You can write this V as the mu into E. Okay. Now this E for is terms from this electric field, which is defined as E is equals to E to E naught is equals to E naught. I'm going to define it cos term cosine 2 pi mu t. I've explained that. Professor Bakshi, Professor Hajar has explained that whenever there is some electric field which is interacting with the water, this electric field is given by this. So the perturbation that is happening due to this electric field of this light can be defined as mu into E. And now this E could be represented as E0 cos 2 pi mu into T. So you can see here there is two parameters are there. One is nu, which is the frequency of light, and this time t. There is a constant time t. So as you can see, whenever light is yeah, so you can see there is some time. You can see here that whenever your Hamiltonian was H naught, which was time independent, as soon as you are irradiating it with light, the electric field of the light will interact with it. And what is changing there? In this, the interaction term will be mu into E, and with this E can be represented as E0 cos 2 pi mu t. And so this t is time. So what this indicate that your Hamiltonian now new Hamiltonian of the system, if I represent it as capital H, just capital H, which is a summation of these two factors, H naught and V, this is not time independent. This will be time dependent. Your H will be time dependent. Okay. So your T will be time H, sorry, H will be time dependent. So your fourth option, which is saying that the Hamiltonian of the molecule interacting with the electric field is time independent, but no, it will be not in time independent, it will be time dependent. Okay, so this cannot be the correct answer.
Dependent.
Okay,
Yes.
got it?
Okay. Yes. What will be the right
Yeah, okay,
answer
okay,
then?
I will discuss that. I'm just going step by step. Okay.
Okay.
Okay. So the another two options, which is so suppose I'm getting this option, the electric field acts along the dipole moment of the molecule. This is not true. There is no such evidence. The electric field will always act uh, along the dipole of the molecule, and also you can see that electric field is not constant. It will change with the time. Okay. Now, whenever Professor Hajra has explained this one, he says that in case of light matter interaction, when the Hamiltonian of the unperturbed system is added by a potential energy term due to electric field, he made two assumptions. Okay, that your t at t times zero, there will be H0. But when there will be t greater than zero, there will be no, there will be a term which will add to this H0, which will give the new Hamiltonian for the system, which is defined as H. So he made two assumptions that this t will be greater than zero, and another assumption was the perturbation is small. The amount of perturbation is causing a very small perturbation to the system. This was the assumption. These two assumptions was made, and then he has calculated the about the transition. He has calculated transition dipole moment, etc. So your answer will be the first one, that the electric field causes a small perturbation to the molecular Hamiltonian. It was then considered as the assumption. So it will be your right answer that this electric field causes a small perturbation to the molecular Hamiltonian. Fine.
Yes, sir.
Okay. So it is the third question. The probability of a light-induced transition from one state to another of a molecule is directly proportional to the square of the dipole moment of the molecule, the square of the overlap between the wave functions of the two states, the energy between difference between the two states, and the square of the transition dipole moment integral associated with the two states. So what should be the answer?
C option will be there.
C. The energy difference between the two states.
The energy difference between two states. It is directly proportional to
Okay,
this one.
so you can see here that is directly proportional. It is it. Okay, I will explain. Okay. Next, others, other answers. So okay, fine. So I am going to explain that the probability of transition between two states, psi I and psi j, is proportional to some term which is called transition moment integral. How it is given? You can see. You know this equation. Professor Hajar has explained that. Yeah. So if my steady state population is A2, in A2, which is a function of simple time, sorry, time. Let me, someone is want to join that. Yeah. Yeah. So A2T is can be given as yeah, A2T This a to t can be written as half mu z on z direction. When it's what 2 1 into e 0 z into, there will be some term, a bracket, that will be e to the power I to the power I into e2 e2 minus e1 minus h nu into t by h cross, this is divided by h cross minus 1, this whole will be minus 1, and this will be, that should not be that much, yeah, that much is enough. So in the numerator what, e2 minus e1 minus h nu. So this is the final equation you have seen. Just 1 minute. Yeah, so this was the equation that Professor Hajra has shown you, that how the what is the probability of transition between two states, and the population of the A2 state. You can define it in these terms where you have every symbols have their usual meanings. Okay. So every term has their usual meanings. Is half mu z into 2 1 e0 z into e to the power I e2 minus e1 minus h nu by into t by h cross minus 1 divided by h2 minus e1 minus h nu. Okay. So what is mu z? Mu z is too much problematic. Mu z is defined as mu z 21, where here it is written mu z 21 is nothing but, can be written, you have seen this direct notation. In direct notation, I can write this as mu2, sorry, psi 2 into mu z psi 1. Yes, that one. So mu z, if you can see this in the derivation, yes, Professor Hajra has taken this term has arisen, that psi 2 mu z psi 1, which he has taken as shortcut as mu z to 1. This term is called transition moment integral between states of 2 and 1. So you can see that this 2 will be in the bra side and this k1 will be in the ket side. Okay. So you have seen the bracket notation. So I am writing this in terms of in a bracket notation there, so that you can easily understand that. So this is the transition moment integral. This is known as transition transition moment integral. Pardon me for my handwriting. You can understand that this is I have written that transition moment integral. I am writing it clearly. So this is transition moment integral. Okay. Now, if you want to find what is the probability of transition between two states, psi I and psi j, you have to find A2. For A2 to find, if you find A2, then you can find that what is the probability of transition. Fine. So for that, you can see here it is directly proportional to which factor? It is directly proportional to mu z to 1. But it is inversely proportional to what? This energy difference between the two states. What I was telling that it is inversely proportional to that term. This is the energy difference between two states. Okay. So it is inversely proportional, or also you have some e term, some energy difference terms in the exponential. So it is not directly proportional to that. It is directly proportional. First and foremost condition for your transition to be there is a probability of your light into transition that, or you have to have the transition moment integrals below 0. Okay, so that's why it depends upon the transition moment integral. Okay. Now, when you are just getting this probability,
Yes.
this is actually the population. Sorry.
Okay, sir. No
So
problem.
if you are going to find the probability, what is the probability? You for this you need to square it up. Okay. So you have to find if the probability, this probability will be is equals to A2 star. You know what I've discussed in the last assignment that the probability can be defined that in this way that A2 star into A2. Since A2 is not a complex number, so I can take you can also take this complex conjugate. Also, it is good. But what I'm just trying to say that if you are squaring it up, then there will be some term which will be like this. That there is no complex term. This will be mu z square, right? Mu z 2 1 square. In this, and what about this part? This will change. That I am not clear because I want to find. I have seen that A2 is directly proportional to mu z. Now, when I'm going to find this probability, I need to square it up. Okay. So for this, when I have to go to square, you can see that this mu z term will be squared up. So the probability of a transition will be the square of the dipole moment of the molecule. No, it will not be the square of the dipole moment. It will be the square of the dipole transition dipole moment integral associated with the two states. Okay, so it will not be the square of the overlap between the wave functions. So if it is saying that the square of the wave overlap between the wave function, that means it is saying about this one, this psi 2 psi 1. It is not like that. It is there is a mu term there, so it is proportional to this term, this mu z to 1. Okay, so your correct answer will be the square of the transition dipole moment integral associated with the two states. Fine.
Yes, sir. Yes.
So moving to the next question, for the normalized wave function psi, which is defined as psi is equal to C1 phi 1 and C2 phi 2. You know what is this is called? This is called, I'm writing here, psi is equals to, I can write psi in terms of this. This is called linear combination. Okay. So if you are going to study a lot of quantum mechanics in your next time, or whenever you are going to study, you will use this one, this C1 phi 1 plus C2 phi 2. That means you are defining a state which is composed of two different states and different contributions there. Okay. So I am defining psi. My psi is C1 phi 1 plus C2 phi 2. Okay. That is my, it is a linear combination of two different states having their wave function phi 1 and phi 2. Okay. And there it is explained that it is complete, psi is normalized. Psi, it is normalized. Just a minute. Someone is trying to join again. Okay. So it is mentioned here that psi is normalized. Fine. And psi can be written as C1 phi 1 plus C2 phi 2. Okay. Where what is phi 1? Phi 1 is a some stationary state and phi 2 is also some stationary state. And C1 and C2 which is constant. And the question is, what is the probability of finding the system in phi 1? You have to find what is the probability of the system we found in phi 1. Should it be C1, just mod C1? Should it be mod C1 square? Should it be 1 by C1? Should it be 1 by C1 square? I have explained this same thing, the same question in the previous question. Here we have the same problem. I have solved it. So can anybody tell me what is the answer?
One by C1.
1 by C1. Okay. Anybody else? Anybody else?
Either 1 by C1 or either 1 by C1 square.
It should be 1 by C1 or 1 by C1 sir, right?
Either,
Either. Okay.
either.
Anybody else?
Yeah, yeah.
Okay. So I'm going to explain that. So you can find this answer in reference numbers in the reference with lecture number 6. You can find clearly this answer. So what I am going to tell you that you can find the probability is defining as this one. I'm going to prove that. Okay. So first of all, you know the answer, then I will prove how it is coming. Okay. So the probability is C1 star C1. That means if you are want to find this psi phi 1, since it is associated with this constant, which is its contribution towards this psi, it is contributing C1 amount to the psi, then its probability that the particle will be in phi 1, which is given by psi 1 C1 square. Okay, that is C1 star C1, and since they are real numbers, so we can say that this is C1 square. Actually, what happens that probability, just writing it here, so I'm taking this side. Okay, so probability that probability that the system is in phi 1, yeah, phi 1 is given by given by suppose I am taking it as P, it should be in bracket phi 1 as I shown in the last question, that probability becomes the contribution square. So I'm going to show you phi 1, sorry, you need to find this one and then you have to square that. This is the general formula of finding the probability the system in state psi I. Suppose I want to find the probability of a system which is composed of, like, if you have your psi is C1 phi 1 plus C2 phi 2 plus C3 phi 3 or dot 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 Ci and I, Ci phi I. Okay. So you want to find that what is the probability that the molecule is or the particle is in the state phi I. Okay. For that you have to find that this part, this will be then phi I, this will be your phi I. Then you have to find this value. In the brass side there will be phi I and in the ket side there will be psi, actual psi. You have to find this value and you have to square that. Then you will get the value of your the probability that the particle in the is in the state phi I. Okay. So now we first need to find this value. Okay. So I am writing this one. This is phi 1. Just a minute. So you have to find what you have to find. You have to find this phi 1 psi. Okay. So you can find this. I am writing here. There, since there is only two parts, phi 1, and I am writing this one as C1 phi 1 plus C2 phi 2. I am just replacing this psi with this C1 phi 1 plus C2 phi 2. Okay. Now I can separate all the terms. So my first term will be phi I C1 phi 1 plus phi 2 Okay, so I can separate these two terms. I have two terms, that is my psi is built up of two terms. One is C1 phi 1 and one other is C2 phi 2. So I am just separating these two terms. One term will be my phi 1, C1 phi 1 plus my second term will be plus C phi 2, C2 phi 2. Okay, suppose, now how can I do that? Suppose if there was no bracket notation, what I should write? I would write it as integration minus infinitive to plus infinitive. There will be phi 1, there will be psi d down. Okay. Now, if my psi will be in, I can write in two terms. I can separate this in integral. Suppose I have in integration of a into b plus c. I can write it as integration of a into b plus integration of a into c. Just the same thing I have done. Now, what I'm going to do, since c is constant, I can take it out. Sorry, sorry, I have made a mistake. Nobody told me. The need to be 5-1. This will be C2 into, I will define it as phi1, define it as phi1. Another one is this will be phi2. Okay, just a minute. I'm just writing it again. This phi1, there should be some phi2. Yeah. So I'm putting this expression C1 into phi1 phi1 plus C2 into phi1 phi2. How can I remove this term? Because suppose in integration you will have phi1 into C1 phi1 into d tau. So since C1 is constant, you can take it out of the integration. Okay. So you can write then C1 outside phi1 d tau. Okay, you are getting my point? That if you have this phi1 C1, suppose, right? Yeah, you can write it here. Suppose in your integration minus infinitive to plus infinitive, if you have suppose phi1, then you have C1 phi1 data. Okay, so if it is the same thing as this one, this is the same thing like this one. Okay, the phi1 C1 phi1 data. Since C1 is a constant, you can take it out always. So you can write it as phi1 phi1 or C outside. The same thing is happening for C2 phi2. The second part, that you have phi1 C2 phi2. You have just taking a C2 out, C2 into phi1 phi2. Now you know this phi1 is normalized. So how should we? This will see. This will be a like a Kronecker delta. You know about Kronecker delta? Kronecker delta is like your two-wave function. Sorry. Yeah. Do you know about Kronecker delta?
No.
Okay. Kronecker delta. Okay. So Kronecker delta says that your two-wave function, if phi1 phi I, suppose I am writing it phi I, another I write as phi j, I can write this thing in this term, delta I j. Okay, so this delta I j, if I have this thing that on my bra side there is phi I, in the my get side there is phi j, then I can write it in terms of Kronecker delta, which is known as phi delta ij. Okay, what is the property of this Kronecker delta? So I think I should take a new slide to explain this little thing, which will be beneficial for many of you. Yes, so I can take a new slide. Yeah. So what I was explaining about that Kronecker delta. Okay, Kronecker Kronecker delta. Kronecker delta have just two values. Okay, always remember. So Kronecker delta when I will use I, since I have a function like phi I, phi j, like this, I can write this as Kronecker delta and I j ij, and this will have two values. Okay, so either it should be equals to I equals to j, there should be a condition I equals to j, and there could be, and it could be possible that I is not equals to j. Just two conditions. Okay, so one condition will be I equals to j, one condition will be I not equals to j. So phi I and phi j, I can write it as in this way that one phi I is in the bra side and phi j is in the kit side. So I can write it as Kronecker delta ij, and Kronecker delta has two values. Either it will be I equal to j and I depends upon whether I is equal to j or I is not equal to j. Okay. So if I equal to j, you can see here, if I am replacing it with phi I, you can see this is in the normalization thing. Phi I. Okay. So you know that in case of normalization thing, this value becomes 1. Okay. Whenever I is equals to j, you can see that there will be thing like phi I in the plus side, phi I in the kit side. This will be replaced by phi I. You can see that this is like just like the condition of normalization, and so it will be 1. And if I is not equal to j, then this will follow orthogonality condition. So under orthogonality condition, this two wave function will be 0. So either they will be equal or they will not be equal. If they are equal, they will follow normalization condition. If they are not equal, then will follow orthogonal condition. Okay. So you can understand how what is the Kronecker delta? Can you understand? Okay.
Yes,
So it will have two value, either 1 or 0. Okay. Now you can tell now what will be the value of this one. So now you can tell me what should be the value of this one. Can anybody tell one? Phi 1, phi 1. I equals to j. So what will be the Kronecker delta for I equal to j? What will be the Kronecker delta for I equal to j? I have written that. I have written that for I equal to j, this value will be 1. And if there is I not equal to j, then value will be 0. It is the same thing. You can see that here is phi I, phi j. There in your case it is phi 1. Either it is phi 1, phi 1. Two types of bracket notations are there. Phi 1, phi 1, or it could be phi 1, phi 2. Or it could be phi 1, phi 2. So if phi 1 is equal to phi j, I have said that this value will be equals to 1. If phi 1 is not equal to phi j, I can see that 1 is not equals to 2, phi 1, phi 2, this will be orthogonal. So if for both the things when they are same, the value will be 1. When both the things are different, the value will be 0. Now I'm going to put that here, here your phi 1, it will be 1. So your value will be C1 plus, you can see this phi 1, phi 2, what I have calculated in the next slide, that it is nothing but equals to 0. This is equals to 0. So 0 multiplied by C2, it will be 0. So what is my value of phi 1 in delta? This thing, I'm getting it as C1. Fine. Now I have to, I'm not stop, I cannot stop here because I have to calculate the probability, which is P is equals to this one square, this term square. So if this term comes out C1, my probability will be C1 square. Okay. And so if C1 value could be positive or negative, so I can put a mod here because C1 can be positive, it can be negative. So I have to put a mod here, C1 square. This will be my probability. Okay. So what will be the answer? Answer will be this one. Okay. This is your answer. Got it?
C square answer is
Yeah. Sorry.
answer is
Yes.
C1
C1
square.
square. C1 square is the answer. I have proved it. You can see here. I have proved it.
Yes.
Okay. So if you have to find that what is the probability of the system to be in the state phi 2, in the phi 2. So what will be your answer? Just like phi 1, if I say that what is the probability of finding the system in the state phi 2, what will be the answer?
Only C1 in that condition.
No, in phi 2, I want to say that what will be the probability to find in phi 2? Phi 2's contribution is C2, right? So when you will do this, the same thing, phi 2 and psi, you can see that there will be condition phi 2, phi 1, another will be phi 2, phi 2, right? Just you are when you are replacing this phi 1 with phi 2, the same other same are remain same. When you are replacing this phi 1 with phi 2, there will be condition, it will come at here, that will be this phi 1 will be replaced by phi 2, so phi 2 phi 1 plus C2 phi 2 phi 2, right? So here your phi 2 phi 1, since I is not equal to j, what I have said here, so this term will get 0, this term will be 0, then and then this phi 2 will be there, which will give you C2. So you will get this term in terms of phi 2. If you are going to calculate, this is in terms of phi 2, you can write it other top here. If you are going to find phi 2 psi, you are going to find that you will end up with getting C2. Okay. So your probability will be C2 squared. You can get it. Fine.
Yes,
Okay.
sir. Fine. Continue.
Okay. So this is the next question. The light-induced transition from one state to another is most intense when which of the following condition is satisfied? The energy associated with the light equals to the energy of the ground state. The energy associated with the light is much greater than the energy difference between the two states. The energy associated with the light is equals to energy difference between the two states, and the energy associated with light is equals to average energy of the two states. So from these four options, I can think of, this is a simplification, that the energy associated with light is equals to what thing? Okay, is it equals to the energy of the ground state, or much greater than the energy difference between two states, or equal to the energy difference between two states, or equal to average energy of the two states? So in what condition the intensity of the transition is much more or maximum? Okay, so what should be the answer? Okay, let me give you some hint, and then you will understand. Okay,
Okay.
yeah.
Yes.
So I have what I have explained you, that the probability at the that the find the that the excited state is populated. You can give it. I have proved that it will be given by A2 square, right? So A2 square I have written in terms of A2 star into A2. Okay. So I'm just writing the final expression where you can see. Just a minute. Yeah. Yeah. A2 square mod A2 square. I'm only interested in the value. So proportional to, I have seen that the probability is proportional to mu z. So this looks like, but this is not m. This is mu. Sorry. Yeah. So this is mu z 21 square. Okay. And there will be some term like e to the power I e2 minus e1 minus h mu to t. I'm just write the expression. You can see in the lecture, this expression was very derived very I mean using some good mathematics. Professor Arjun has derived that. So it will be like E2 minus E1 minus H nu. So it will be also squared up. And this term is also squared. So I cannot take this. You can take it in. Yeah. Hmm. Yeah. So this is a multiplication of these two terms. Okay. First one is transition moment integral, and the second one is e to the power I e2 minus e1 minus h nu into t by h cross minus 1 by e2 minus e1 minus h nu whole square. Now this is the hint that I am showing, that you have to find in which condition the intensity will be maximum. When will the intensity will be maximum? When there will be more number of particles in A2. So you have to find the population of A2. So under that condition, that A2 square is highest, if in that condition A2 square is highest, in that condition you will get most intense transition. Okay. So for A2 square will be highest, your first time you know this transition moment integral, this will have a certain value, but there you can, from the second time you can say that what condition your uh, intensity will be maximum. Now can you guess under which condition? From the second term?
Second option will be there.
much greater than the energy difference. Okay, okay, I understand. So you can see here that it completely depends upon this term. This depends upon this term. Okay. So since it is in the denominator, if it is decreasing, A2 is decrease. If it is sorry, if it is decreasing, A2 will increase. If it is increasing, then it will decrease. Right? So lowest value. So for intense transition, I write it here for intense transition, this will be very low. It will be, if it is low, then 1 by this one will be high, right? Suppose you have 1 by 2, you can get is 0.5, right? If you have 1 by 0.2, 0.2, then you will get 5. If you have 1 by 0.02, you will get 50. Okay. So as you are decreasing this new numerator, this lower one, this one, as it is actually gradually decreasing, your this total factor is increasing because it is in the lower side. Okay. So its lowest value will be, what will be its lowest value? It cannot be less than 0. Okay. So its lowest value will be equals to 0 when you will have maximum value. That means this E2 minus E1 will be equals to, the lowest condition, it will be equals to H nu. So this delta E is equals to H nu. Okay. So this is the condition under which you will get most intense emission. So this condition is clearly showing that your energy difference between the two states, pointer, your energy difference between the two states will be equals to the energy of the light. Okay. Under that condition only you will get highest intensity transitions. So most intense transitions actually occurs from a state with energy E1. Yes. Energy E1 to a state E2. If it follows, this is called Board frequency condition. Why I mentioned in the beginning that Board frequency condition is the energy difference between two states. It is very much important in spectroscopy point of view that the energy difference between the two states E2 and E1, it should be equals to H nu. That is the energy of the light. Nu is the frequency. When it is multiplied by Planck's constant, it will give you energy. So which one is correct? Energy associated with light is equals to energy of the ground state. No, it should not be energy of the ground state. Much greater than the ground state. No, that will give you some intensity of absorption, but that will be not the most intense one. Okay, so most intense one will be the energy associated with light is equals to energy difference between the two states. Okay, so it is your correct answer.
Okay.
Okay,
Okay.
okay. So I'm going for the next one. Yeah, there is some change that correct form of Beer-Lambert law. We have learned about absorption in absorption spectroscopy. This is a very basic law for, okay, let's write it here. Yeah, so you can find this answer here. Lecture 8, Lambert Beer law. We'll spend some time here. because this is very fundamental and you can easily solve questions from here. Okay, Lambert-Beer law. So what is Lambert-Beer law? Which should be the answer? Is T is equals to epsilon CL minus log T is equals to epsilon CL log A is equals to epsilon CL or log I0 by IT is equals to minus epsilon CL? What should be the answer? Correct form. Which should be the correct form?
Log of I0 minus IT that equal to this.
This fourth one?
Yes, fourth one.
Anybody else? No.
Okay, so please explain that one.
Yeah, I will
Please.
explain everything. Okay, don't need to worry. Yeah, but I am
Yeah.
just waiting for some other responses. Yeah. Okay, so I'm going to explain. Here is your Lambert-Beer law, which states actually, yeah, so your Lambert-Beer law states, yeah, that A should be equals to epsilon CL. Okay, so your A Lambert-Beer law states that absorbance can be written as this form: A is equals to epsilon CL, where this epsilon is called molar extinction coefficient. C is the concentration of the sample, and L is known as the path length. Okay. Now, in your four equations, there is no mention of A. So you have to convert this A to some other term which is related to this T or I0 by IT, and then you have to match with this A is equals to epsilon CL and see which one is giving you the correct thing. Okay. For that, suppose suppose this is my sample chamber. Wherever I have some sample, I am giving some light. Yeah. So some light is passing through this sample. It is coming out, and there is some molecule which is actually absorbing some light. Suppose I am giving I0 intensity of light. Okay, the light I am using for this molecule, it is I0. Okay, so there will be some molecule which will absorb this light. So after that, the I intensity that I will get is IT. Fine. So this ratio IT by I0, that means vast amount of light is transmitted, IT by I0. Okay, so this is defined as transmittance T. Okay, now absorbance is related to this phenomena by this relation. A is equals to can be defined as log of I0 by IT. A is really can be defined as I0 by IT. Okay, so you can define your A as log of it would be I0 by IT. Fine. Now you can see here I have just written that I can say that transmittance can be defined as IT by I0. Now in absorption equation, what I'm seeing that log I0 by IT. So you can know I can replace it with log 1 by T. Mhm. Because here there was IT by I0, here opposite thing I0 by IT. I can replace this t with 1 by t. So what should be the relation now? So your a will be now log 1. You can know log a by b, you can write it as log a minus log t. The same thing will happen here, log 1 minus log t. So you know your log 1 is 0, nothing but 0. Log 1 is nothing but 0. So your final answer will be your a should be equals to minus log of t. So this is the relation between the absorbance and the transmittance. A is equals to minus of log of t. Yeah. So you say a should be equals to minus of log of t. Now if you can replace this a here by minus log t, you can see you can find this equation, right? A is equals to minus log t and minus log t is equals to epsilon c here. So this is another form of Lambert-Beer law. The first one is not correct, but I have proved that the third one is not correct. But what about the fourth one? Someone answered that fourth one. But fourth one, if you log I0 by IT, this will give you A. So this will give you A. Correct? Then there was a negative sign. Minus epsilon CL. It was not minus epsilon CL, so it could not be possible that A is equals to minus epsilon CL. A will be equals to epsilon CL. Got it? So your correct answer will be log minus log t is equals to epsilon CL. Fine?
Yes.
So this is the next question. Aqueous KMNO4 is purple in color and given that it follows Beer-Lambert law. What is Beer-Lambert law? I have explained that in the previous question that A is equals to Lambert-Beer law. It is required everywhere. Okay. Lambert-Beer law or Beer-Lambert law, you can call it anything. Okay. Yeah. So you're with the every symbol have their usual meaning. I can write it as A is equals to epsilon CL. Okay. So your aqueous cheminophore is purple in
Yeah.
color and it follows Beer-Lambert law. So now your question is a plot of absorbance against concentration. What kind of plot it will be? Is it linear with a negative gradient? Is it linear with a positive gradient? Is it exponential or non-exponential, non-linear? So what should be the answer?
That should be linear with positive gradient.
Linear with positive gradient. Okay.
Gradient.
Any other? Okay, fine. So this is the correct answer. You can see the same thing I have written here. Your main equation is A equals to epsilon CL. Okay. Now you have asked to plot. You are asked to plot a A versus absorbance against concentration. You can see in the question that is again absorbance against concentration. Sorry, absorbance against concentration. Okay. You have to plot just like y versus x. So in y-axis there will be absorbance, and in x-axis there will be concentration C. So you can see from here, you have to plot this A against C. I'm just rearranging that, so you can just rearranging this L I am putting in there into C. I can write it epsilon into L into C. You just compare this with this equation.
Yes, both are
Yeah,
same.
you can just compare with this equation. What is this equation? This is equation of a general
Yes.
equation of a straight line, right? So in this case, if you compare with it, you can see that this is not this C, okay? This is general equation for straight line. So in this case, for Lambert-Weir law, there is no C. That is, your intercept is 0. But if you compare these, you can see that what is this M in this general straight line equation? This is the slope, or this is the gradient. Okay. So in this equation, if you can compare, you can see that your slope will be epsilon into L. Fine. So your slope will be epsilon into L. Now I am going to plot this absorbance versus concentration. So I can follow this equation of straight line, and you can see that since C is 0, so I will have no intercept. So in my case, whenever I am going to plot this absorbance against concentration, there will be no slope. Sorry, there will be no intercept. So my straight line will follow the origin. So why I am writing this positive slope? Because my epsilon and L both are positive numbers, right? Your path length cannot be negative. In epsilon, this is molar extinction coefficient, it cannot be negative. Fine. So your slope, it cannot be negative, non-zero slope, negative, non-positive slope. So your slope, the positive slope. Okay. So what will be your plot? Nature of the plot, this will be linear with positive slope. Slope is also gradient, you can say, linear with positive gradient. This is your final answer. Got it?
Yes, sir.
Okay. So I'm just a quick query about if the three or four of you are there. Just quick question. If I put epsilon in the y-axis and the concentration in the x-axis, what will be the type of graph? Just a quick query. If I have to plot, someone says that you have to plot epsilon against concentration. So what will be your plot?
That will be the negative one.
Negative one. Okay. See, this epsilon, which is known as molar extinction coefficient, molar extinction coefficient, it is actually the function of lambda. That is the light wavelength you are using. If you change lambda, your epsilon will change. Okay. So it will not. It is not interacting with this concentration. It is not interacting with the path length or absorbance. It is just interacting with the wavelength of the light. So whenever you are changing the concentration on a fixed lambda, epsilon will change or not?
Will change.
How can will change? Because it is a function of lambda only. You have a fixed lambda. You have fixed the light. You are just changing the concentration of the substance. And epsilon is not a function of this constant concentration. So will epsilon change now?
No, no.
No,
In
it
that
will not
condition, it
change.
will
It will
not
change
change.
with the lambda.
Ah,
That is the light.
will change with the lambda.
Yes.
Yes, sir. With the
So
lambda.
your concentration with epsilon will not vary with concentration. Okay. This is just quick query. Just I have asked.
That means it is exponential, huh?
Hmm?
It is exponential in that condition.
No, no, no. Exponential
Apart
is
from that
different.
full
There
option.
will be some e-20 bottom. This will not change with concentration. So this will be the straight line, just a straight line. It will not deflect or it will have no slope, zero slope. Okay.
Okay.
This will have a
Okay.
fixed value. This epsilon will be fixed value for every concentration. Okay.
Yes. Yes.
So now you have to find the unit of absorbance. Anybody tell me what will be the unit? This is a very pretty simple question. Of
Molecule square
molecule, no, this is mole. This is
divided by
not
dm.
molecule. This is mole. Okay. Yeah,
Mole.
mole,
Yes. Sorry. Sorry. Mole.
mole, and
Mole and
unit.
dm
The
cube.
first one, nothing. Okay. Let's see. You are right. See, I am writing all the things related to absorbance. Absorbance. Okay. I've written this A. I can define this A. Can be defined as oh, I've defined this A. This can be defined as log of I0 by IT, which is equals to epsilon C into L, which is your Lambert-Beer's law. You can find its reference A, lecture 8. You can easily calculate that. So for calculating the unit of absorbance, you just need this equation. Okay. From this equation, you can easily calculate it. So you can see, starting it again, A is equals to log of I0 by IT. Here you can see that I0 and IT. What is I0? Intensity of the incident radiation, right? And what is IT? That is the intensity which is coming out from the after
Transit.
the absorption, right? So both the term I0 and IT, which what it does it represent? Both represent intensity, right? So your I0 and IT both have my pen. Yeah. So your I0 and IT both represent intensity. Both represent intensity. Okay. So your absorbance is a ratio of two intensities, and then you have to take the log, right? To calculate this absorbance, you have to take the ratio of two intensities, that is the intensity of the incident radiation and the intensity after coming out of the sample chamber. So since it is a ratio of these two intensities, so it will be this thing. And if you are taking log, then it will be again some unitless thing. So your A, this absorbance, this will be some number just, and it will be unitless. Okay. So since your absorbance is log I0 by IT, since it is a ratio of two, two intensities, it is a ratio of two intensities. So it will just, the units are same. Since it is a ratio, so it will, the units are same, so it will cut out. And if you're taking log, so your AB will be a unitless number. So final answer will be the absorbance unit is unitless. Got it?
That means absorbance is unitless,
Yes,
no?
absorbance is unitless. Exactly. It is just a number.
Okay.
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 Okay. So it is the next question, which is talking about the Born-Oppenheimer approximation, which is very briefly mentioned in the lecture by Professor Bakchi, who has explained that if your total energy, you can write your total energy as made of translational plus E of rotational plus E of vibrational plus E of electronic with the sliding relay plus E of nuclear. Okay, so you can treat this total energy as composed of translational energy, rotational energy, vibrational energy, electric energy, and nuclear energy. These energies are magnitudically different, so all of this total will give you this total energy. Now, in this case, you can calculate this energy and you can calculate the wave function by stating that these two, the motion of this nuclei and electron, which is can be treated separately. So, this is called Born-Oppenheimer approximation. So, the Born-Oppenheimer approximation is just a statement. So, it states that the motion of this atomic molecule and nuclei, it can be treated separately. Okay, this can be treated separately. Now your options you can see here, the motion of atomic coordinates of nuclei and electron can be treated separately, right? What I have said. Okay, motion of atomic coordinates of nuclei and electron are coupled. No, they are not coupled. They are can be treated separately. You can take this nuclear part separately. You can calculate this electron part separately. Okay, you don't need to couple those things. Also, what is the third option? Nuclei move much faster than the electron. No, actually, this doesn't happen because nuclei has a higher mass. And the fourth one is actually the opposite thing. The electron has higher mass than the nuclei. No, the electron nuclei has a higher mass. That's why in Born-Oppenheimer approximation, you can think that this nuclei is almost static and your electron is moving. Okay, so these two options will be not correct. So the correct option will be the first one, that the motion of these atomic coordinates of nuclei and electron, this can be treated separately. So this is your correct answer. Got it?
Yes.
Yes. So I'm coming to the last question that I'm going to solve today. That inhomogeneous broadening is given by which type of line shape function? So in the beginning, I was talking about in the lecture 9, Professor Bakshi has explained about these line shape functions. He has explained line shape function. He has explained about the two different types. First, it is Gaussian, and another is, what is another one? Another will be Lorentzian. Okay, these are two different line shape functions which are responsible for the broadening of lines. Okay, atomic lines are broadened by mainly these two. Broadening can be explained using these two different line shape functions. One is Gaussian function, another is a Lorentzian function. Okay, now these two functions are responsible for two different kinds of broadening. One could be homogeneous broadening, another could be inhomogeneous broadening. As you have seen, for homogeneous broadening, actually what happens? For homogeneous broadening, you can see that every atom in your every molecule, or sorry, every atom or every molecule, they are actually facing the same environment. Suppose you are giving pressure to a system. Okay, so every molecule that is present in the system will feel the same pressure. Okay, so their line shape will be actually deviated. Their line shape will be broadened, and in good language you can say it is broadened. It's broadened to the same extent. But if so, this is called pressure broadening. Okay, so in that case, pressure broadening, or it could be collision. Okay, pressure broadening, or it could be a collision that you are bringing about collision between different molecules. So the environment will be same for everyone, though that in that case you will expect a Lorentzian line shape function. Okay, your line shape will become a Lorentzian one. So in that case, for homogeneous broadening, if there is a responsibility of pressure and collision, and which will give me a line shape function which will be Lorentzian in nature. But if there is some Doppler effect, you have laid Doppler effect in sound. Okay, suppose a train is coming from far away. When it is coming, it is whistling from far away. When it is coming to the station, you are situated. You are standing at the station. You are just listening to this sound of the train. It is gradually increasing, and then it is getting gradually decreasing. So this is Doppler effect. Okay, the velocity of sound that is appearing to you is much gradually increased or gradually decreased. Fine. So this will give rise to Gaussian function. So this broadening will be inhomogeneous broadening. This will be inhomogeneous broad. So this is what kind of effect is responsible of this for this Doppler effect. Just like the velocity of sound, suppose some molecule is coming to one. I am using some light. Okay, some molecule is coming closer to the light. When this is coming closer to the light, its frequency is increasing. When it is going far away from the light, its frequency is decreasing. So there will be the broadening will be inhomogeneous in nature, and that broadening, that inhomogeneous broadening, is explained using this line shape function, which is Gaussian in nature. So whatever I have told, that homogeneous broadening actually leads to what kind of profile? Lorentzian profile, right? But if you have inhomogeneously broadening, it leads to Gaussian profile. So what will be the correct answer?
First
First
one.
one, Gaussian, exactly.
Yeah.
Okay.
Okay.
Okay. So do anybody have any questions up to this?
No one right now. No one. But you had clearly explained all 10 questions.
Yeah, okay.
That all doubt will get cleared from these 10 questions, whatever the type of that.
Okay.
But we had cleared that one
Okay.
actually.
So if you can try to solve this assignment, I have just done some dummy questions, and if you find any question kind of query, any kind of suggestion, or any kind of problem you are facing, you can just tell me. Okay.
Yes.
Okay. So
Okay. That will be the end of session. No?
sorry.
That will be the end of session.
Yeah. So that will be the end of the session because all the questions I have done. Okay. Okay. Fine. So I'm stopping the recording.